and equipment, section 241. This is the last chapter, chapter 9, which I will explain about the pump. So the objective of this chapter is student to acquire fundamental concept of pump and its characteristic, and then the learning outcomes at the end of this chapter. Students should be able to, one, state the function of pump and its type, and second is characterize the performance characteristic of pump by its capacity, net head, overall efficiency, water horsepower and brake horsepower. And then the last, number 3 is calculate the capacity, net head, overall efficiency, water horsepower and brake horsepower of pump. And then interpret the information from the pump performance curve. And then the last one is discuss about pump cavitation and PSH. So pump is very important mechanical device in industry and agriculture and in daily life. So the functions of pump has two. Okay, the first one is ability to supply liquid at required rate of flow, and then number 2, to supply liquid, this pump will impart an energy to the liquid, so thereby increasing the pressure. So as we know that previously we already calculate the major and minor losses. So let's say we have these types of configuration. For example, we want to transfer A to B. So we have two minor losses here, and then we calculate the major losses where from the Bernoulli's equation. From Bernoulli's equation, we will calculate what is the delta P, the pressure loss in this system from point A to point B, which includes the potential energy, kinetic energy, major losses and minor losses. So this delta P is the amount of pressure that required for that fluid to flow from A to B, and then these reductions or the pressure losses, the amount of these pressure losses will be supplied actually by the pump. Okay, the pump will supply this amount of energy or this amount of pressure. That's why we need a pump. So if the pump impart an energy or impart the pressure here, impart energy or supply the pressure that is below than the delta P, okay, which is not enough to overcome this delta P, therefore the liquid will not flows from point A to point B. So that is the important functions of the pump. Okay, and the ability to supply liquid at required rate of flow, because in the Bernoulli's equation we know that we have to find the velocity. That velocity is actually the velocity for the required flow rate. So if we want that kinds of flow rate, then we have to use the velocity, and after that we will calculate the Reynolds number and we solve the Bernoulli's equation. Then at the end of that Bernoulli's equation, we will find that that amount of delta P will require for this flow to flow from this liquid to flow from A to point B. Okay, so this is the diagram of the pump. That figure 1A is the diagram, a simple diagram of the pump. If you see these kinds of diagram in your piping system or in the internet when you try to search information about the pump, so these kinds of diagrams will appears. So you do not have to worry. This diagram is a standardized diagram for the pump. So this is what I've say that the important function about the pump, where the pump will have a rotor here, where we have the energy supplied to that rotor, and then that rotor will create will transfer that electrical energy to the mechanical energy. So after that, the mechanical energy will transfer to the pressure energy, then it will flow, the fluid flow the fluid from, let's say this is point A to point B. So the fluid impart energy and then transfer electrical to the mechanical and then mechanical to the pressure energy. Then it will flow the fluid from A to B. Okay, that is the functions of the pump. So there is a difference between the pumps, turbines and compressor. So you will see these kinds of equipment in the chemical engineering. So for the pump, it adds energy to the fluid. So when you add the energy, then the fluid do the works. So for the turbine, it will extract energy from the fluid. So the fluid, for example, the turbines will be used in thermal power, hydroelectric power, where that electric comes from the conversions of energy from the water, and it will change to the mechanical, and then the mechanical will change to the electrical energy. Pumps, from the electrical energy, it will change to mechanical, and then it will change to the pressure energy. So for the turbines, it vice versa. Okay, when used with gases, pumps are called fans. So for the turbines and the pumps, normally we will use fluid, liquid. Okay, but for the compressor, for the gas, we will use fans, blower or compressor. It is much more suitable for that kinds of for gases. Okay, so basically in the pumping system, we have main pump components, pumps, we have prime mover. This is the components in the pump. We have pumps, prime movers, either it is electrical motors or engines or air system, and then piping to carry fluid. So for the pump, we have prime movers and all of that, so that we have a pumps, and then to connect between the point A to point B, where we want to flow the fluid from A to B, we have the piping to carry fluids. And then we have valve to control flow in the system, and other fittings, control instrumentation, other fittings such as 90-degree bend or globe valve or other piping components. And then end-use equipment can be used to heat exchangers, tanks, hydraulic machine. So, or for the fluid, for example, when for example a Ranhill SAJ wants to transfer the liquid from dam to the to water treatment plant, they will use pumps. Then okay, they will use pumps to transfer from the dam to the water treatment plant, for example. Okay, we have types of pump. So first is positive displacement pump. So use changes in volume in combination with valve to move the fluid through the pump. So mode of operation, so pump has a revolution, so each of the pump revolution will transfer a fixed amount of liquid. Okay, it will transfer and then positively discharge at the end. So if pipe block, what will happen? So the pressure rises, can damage pump. So example is bicycle pump or some car oil pumps, the hard peristaltic pump. So I will explain about the peristaltic pump. So this peristaltic pump have these kinds of shape. So in the pump, so we have this tubing. Okay. So what does it means that for each of the revolution, this is the pump prime mover, so it will move. Okay, and each of the move, it will transfer a fixed amount, so it will press this tubing, and then it will transfer the water or the liquid up, so it will transfer positively upward. So then the next the next will press this at this tube, and then it will transfer another a fixed amount of liquid upward. So it will continuously move, rotate, and each revolution will transfer a fixed amount of liquid. So rotodynamic pumps, rotating impeller converts kinetic energy into pressure or velocity to pump the fluid. So for example is centrifugal pumps. So I will explain a little bit more on the centrifugal pumps after this. So this is centrifugal pumps. So the mechanism of the centrifugal pumps is one of the simplest pieces of equipment in any process. So the liquid will be forced into an impeller by atmospheric pressure. So this pump is actually in a lab. So for those who go to the lab will see these kinds of pumps in the labs. Okay, each of the equipments use centrifugal pump. So the liquid is forced into an impeller. So this is pump. So we have pump, and then this is the configuration in the lab. So we have tank here. The pump will suck the water. The water will transfer to the pump and positively displace the liquid upward. Then what will happen? This liquid is forced into an impeller by atmospheric. This tank is open to atmosphere. So then we have the pressure that will rise to this point, and then it will transfer the water into the centrifugal pump. So this transfer will be in axial direction. So or maybe this will be transferred by the jet pump or artificial pressure. So the vanes of impeller pass the kinetic energy to the liquid, thereby causing the liquid to rotate. The liquid leaves the impeller at high velocity. So this vane will rotate. So the rotations of this vane, when the fluid moves to this vane, and this vane will convert the kinetic energy to the liquid, and then the kinetic energy, the liquid will transfer to the volute casing. So from here the liquid will move axially to this pump, and then as it rotates, it will change the kinetic energy to the pressure energy. So the volute casing will convert the kinetic energy to the pressure energy, and as it rotates and then transfer to the volute casing, change to the pressure energy, and then it will move the fluid upward. Okay, the impeller surrounding a volute casing, or in case of turbine pump, a stationary diffuser ring, the volute or stationary diffuser ring converts the kinetic energy into pressure energy. Okay, that is the mechanism for the centrifugal pumps. So for the capacity of the pump over volume flow rate, okay, that is Q. The equation is mass flow rate over density. So for the performance of the pump is characterized by net head H. So this equation is actually from the Bernoulli's equation. We know that the Bernoulli's equation is P1 over rho G plus U1 square over 2G plus Z1 equal to P2 over rho G plus U2 square over 2G plus Z2. This is the general Bernoulli's equation, where we have some of the assumption to be made in order to use these kinds of equation. But after that, we go to the chapter 8. This Bernoulli equation has been at another one term. So Bernoulli's equation will becomes P1 over rho g plus U1 square over 2g plus Z1 equal to P2 over rho g plus U2 square over 2g plus HF. Okay, this is the chapter 8 where HF is a major and a minor losses. Okay, so this Bernoulli's equation, general Bernoulli equation, assume that there is no friction. It is a frictionless. And after that, we go to chapter 8. We know that we do not assume that system is frictionless. Therefore, we have to add the major and minor losses. So after that, in chapter 9, we have to add another terms in Bernoulli's equation. Okay, so P1 over rho g plus U1 square over 2g plus Z1, you have to add plus HP equal to P2 over rho g plus U2 square over 2g plus Z2 plus HF. So this is new Bernoulli equation where we include the horsepower, we include the head of pump. So actually this equation do not include the HF. So this system is assumed that there will be no friction in the system. So the efficiency of the pump will be evaluated by using this equation. Okay, omega T shaft is a brake horsepower, where normally this work dot shaft will be given in your question. Okay, so please remember this equation. And then the pump performance curve. This pump, as we can see here, we have 3 different curves here. So first is the curve, this curve, black curve, and then the second one is this one, and then the last one is BHP. So the BEP is the best efficiency point, where at this point we have best efficiency point for the pump, okay. And then what we can see here is a shut-off head. So shut-off head is quite high, the head, okay, head of the pump. When the pump has been shut off, the head is quite high here. So what is actually happening here, when the shut off, the Q is 0. The Q will not flows into the piping system, but the pump is still at running. So what will happen? It will increase the head of that system. That's why the Q, the head of this graph at this point shows that head of the pump is at its high when the pump is being blocked. The pump is still running, but the Q is 0. There is no fluid flow into the pump. But the okay, so for this here, free delivery, so at free delivery, Q is at maximum and the head is 0. So what will happen here is achieved when there is no flow restriction. So at the pump inlet or outlet, no load to the pump, so pump does not do any job to that system. So therefore the head is 0, and then the delivery is increased, or delivery is at high. Okay, Q is a very large, but H is 0. The pump efficiency is 0 because the pump did not do any useful works. So that is the pump performance curve. So for the matching a pump to a piping system, you have to remember that we have a system curve. This system curve is developed by this equation, okay, H required, and then this is pump performance curve is from this equation lah, this graph. So shut off the free delivery. So in order for you to find the steady operating point, the H required must be equal to H available, where these two curves will intersect each other. Intercept each other at this point. This is the operating point for a pump. So how to get this equation? So as I mentioned before that this as I mentioned before, we have these kinds of equations. So P1 over rho G plus U1 square over 2G plus Z1. We have to add HP here, head of the pump, equal to P2 over rho G plus U2 square over 2G plus Z2 plus HF. So now rearrange your equation to HP. HP is equal to, so we have P1 over rho G plus U1 square over 2G plus Z1. Okay, this is for in. Sorry, we should have negative here. So plus we have P2 over rho G plus U2 square over 2G plus Z2 and plus HF. So HP is, I rearrange it. So rho G plus U1 square, U2 square over 2G plus Z2. So this is for out, minus P1 over rho G plus U1 square over 2G plus Z1 in, plus I will expand this HF. So H major plus H minor. So this is the equation to determine what is the HP. So this HP is actually H required, okay, in that question. Okay, so you may pause this video in order for you to take note of this equation. Okay, now this is the equation, so you do not have to worry, because since if you refer to this equation, we have alpha 2 and alpha 1. If you refer to another book, this alpha is actually represent either that flows is laminar or turbulent flow. If it is a turbulent flow, that alpha will be 1. So you do not have to worry. Please refer to my equation before that I've wrote just before this for your calculation to determine what is the H pump. So that H pump is H required. So in order for you to determine the steady operating point, H required, that equation must be equal to H available. So normally the H available will be given to you in the question. Either it is directly give you the value of H available, or it will give you the equation itself to determine the H available. What you have to do is equate both of the equation in order to find whatever parameters that they need you to calculate. Okay, it is impossible for you to get these kinds of graph where we have 3 different operating points. So you have to avoid these 3 intersection. So in unfortunate situation, the system curve and the pump performance curve intersect at more than one operating point. So it can happen when the system curve is almost flat. So system curve means that this equation, when you plot into this graph, so you have a flat system curve. Okay, then that flat system curve here, so we'll have a different H available, the point of intersection between the H required and H available. So it is impossible for you to get these kinds of graph. Okay, so please avoid these kinds of intersection three points of interception. This situation should be avoided because the system may hunt for an operating point, leading to unsteady flow situation. Okay, so this is the equation I've already mentioned about before, how to derive that equation. So here we have H turbine, so please cancel out this H turbine, since we are not dealing with the turbine, we are only dealing with the H pump only, because the H turbine will have that Bernoulli's equation will add another terms. Okay, so please remove the H turbine. So this derivation I've already explained to you before, and please refer to that equation in order for you to determine what is the H pump. Okay, so pump head delivered to the fluid does four things. So one, increase the static pressure. So from P1 to P2, the static pressure comes from the fluid itself. So it increases the dynamic pressure of the fluid from point 1 to point 2. And then 3, it raises the elevation of the fluid from point 1 to point 2. So this is referred to this picture actually, this figure. So to from point 1 to point 2, it does it raises the elevation. So after all of these will refer to that delta P. Okay, and it overcomes irreversible head losses in the piping system. Okay, so now we move to pump cavitation or NPH. So when pumping liquids, it is possible for the local pressure inside the pump to fall below the vapor pressure of the liquid. So that pump is the pressure in the pump is below than PV. So what will happen? So before that, PV is saturation pressure. Okay, so what will happen when the P inside the local pressure of the pump is below than the saturation pressure? So it will create bubbles. So this bubble is actually when it raises, okay, it will fill up this pump. So when this pump when it approach to the wall of the pump, it will collapse. So this collapse will make the pump vibrate. So when this pump is vibrate, it will cause a noise. So the continuous formations of the bubbles will damage to the impeller blades. So we want to avoid that kinds of situation. So in order for you to determine what is the pump cavitation, so you have to use this equation. Okay, NPSH. Determine what is the NPSH. Now what we have is P over rho G plus V squared over 2G for the pump inlet minus PV over rho G. So PV will be given in your question. Okay, you just substitute the PV and rho G. But our concern here is the pump inlet here. Okay, do not use these kinds of information in order for you to determine either that pump is the cavitation occurs in the pump or not. We will use this NPSH. Okay, I will explain about this, how to derive the equation and substitute into this equation. So what you have to do, remember, please memorize this equation, NPSH. So to make sure there is no cavitation, actual NPSH should be higher than NPSH required. So you have in the question you will be given the NPSH required. So you have to calculate the NPSH and then compare with the NPSH required. So if it is your NPSH is greater than NPSH required, therefore there is no cavitation. So actual NPSH will be you will be calculated by using this equation. So required will be given in your question. So how to determine how to derive that equation? So we know that the MPSH is only give us that the P over rho G plus V squared over 2G. So this is pump inlet PI minus PV over rho G. This is only this is the equation to determine the MPSH. What is our main focus is to this point. So pump inlet. So we have this pump, and then whatever value that, whatever head or friction just before the pump must be calculated in order for you to calculate the MPSH. So now how to calculate? So this equation will derive from the Bernoulli's equation. So P1 over rho G plus U1 square over 2G plus Z1 plus H pump equal to P2 over rho G plus U2 square over 2G plus Z2 plus HF. Now we are calculating the value before the pump, so therefore HP will be removed from this equation. So P1 over rho G plus U1 square over 2G plus Z1 equal to P2 over rho G plus U2 square over 2G plus Z2 plus HF. So we have this equation. So now my point number 1 is here, number 2 is before the pump. So therefore pump inlet is P2. Am I right? Pump inlet is P2. So whatever P2 value you have to arrange here is P2 V2 square, okay, which means P2 over rho G plus U2 square over 2G, in order for you to substitute into this equation. Okay, let's take a look at it. So P1 over rho G plus U1 square over 2G plus Z1 equal to P2 over rho G plus U2 square over 2G plus Z2 plus HF. So now in the MPSH equation we have P over rho G plus V square over 2G P inlet, pump inlet. So pump inlet is P2 over rho G and U2 square over 2G. So rearrange this equation. So P2 over rho G plus U2 square over 2G equal to, bring all others parameters to left hand side. So rearrange it. So P1 over rho G plus U1 square over 2G, okay, plus Z1 minus Z2 minus HF. Okay, this is your equation, and then I will put it PI. So take out this equation and substitute into this equation. Okay, your MPSH is equal to P1 over rho G plus U1 square over 2G plus Z1 minus Z2 minus HF minus PV over rho G or PV. So now in the question, normally PV given is in absolute. So therefore this P1, if you have pressure here PATM, therefore you cannot remove it or take out these terms and zeroing these terms, take out or zeroing this term, since PV is in absolute pressure. So therefore it will remain P1, and you will substitute the value of absolute pressure here. So you will not use the gauge pressure here for you to determine what is the MPSH. Therefore, for example, here is P1 is 1 atm, 101.32 kPa. Therefore, you have to substitute 101.32 kPa to this equation. Okay, because this PV is in absolute pressure. But for the chapter 8, we will zeroing this term since it is a PATM. Okay, or you have to minus PV. You want to zeroing these terms is okay, but for the PV you have to PV absolute minus 1 atm. Okay, you have to make it as a gauge pressure. Okay, in the question PV given is always in absolute pressure. Okay, you have to minus with 1 atm in order for you to remove this term P1. If you don't want to remove the P atm here, so you have to use the absolute pressure here. If 1 atm, then you can have 1 atm. If your 0.1 is 32 kPa pressure, for example, and then you have to add 101.32 to make it as absolute pressure. Okay, so that is how to calculate the MPSH. This MPSH is actually MPSH required. Then you will compare this MPSH value with the MPSH actual. Sorry, this is the MPSH actual. I'm so sorry. This is MPSH actual, and then the MPSH required will be given in the question. You will compare with these two. If this value is greater than MPSH given in the question, then no cavitation occurs. If the MPSH here is below than MPSH required, therefore the cavitation occurs. So how to increase the available MPSH? This is from the Bernoulli's equation. For example, lower the pump, raise the inlet reservoir level. So when you raise the inlet reservoir level, what will happen to the elevation? It will reduce. The elevation will be reduced, then you will reduce the delta P value. So that delta P will correspond to this MPSH value lah. And then use larger diameter of pipe. So when you use larger diameter of pipe, you will have you will reduce the amount of friction factors of the H major. So when the H major reduced, then the delta P also will be reduced. Then next is reroute the piping system. So when you reroute the piping system, you will actually reduce a few fittings, or you will use shorten length of the pipes. Okay, next is a shorten length of the pipe, since the major losses contributes a lot to your delta P value. And then use motor pipe. When you use motor pipe, the friction factor will be reduced. And then the last one, use elbow with minor losses, minor loss coefficient. When you reduce the fittings in your system, piping system, you will actually reduce a little bit of your delta P. And then that's all for that